Okay, so here we have our picture again. We have V, we have W, we have our null space and our row space in V, and we have the column space over here in W. Now every point in the plane is identified with a vector with the initial point at the origin, terminal point at that point. So here's a point. So it's identified with this vector, and we're going to call this vector V. Okay? That vector V certainly goes someplace over here. Where does it go? Well, it has to go in column space. Okay, there's no choice because the column space consists of all the vectors that you can get by doing this transformation. So that's it. Okay, every vector goes to the column space. Well, what are we going to do with the vector V then? Where's it going to go on the column space? Well, it's actually fairly simple. I kind of need another color, so we'll emphasize it with the red. And I'm going to extend the line representing my column space a little bit. Okay? This vector can be expressed as a sum of a vector in the row space and a vector in the null space, can it? Matter of fact, the row space and the null space, in this case, form a basis, don't they? The basis of the row space together with the basis of the null space is a basis for all of R2. Okay? Well, then I'm just going to draw it. Right here are the two unique vectors that add up to give you V when one vector is in the row space and the other vector is in the null space. Okay, so I'm going to call these two vectors V sub R and V sub N. I'm just trying to figure out where to label it. I should have labeled the thing up there. But I'm going to, okay, I'll do it here. Not a very good place, but okay, I've got a V sub R and a V sub N. V sub R is in the row space. V sub N is a vector which, if drawn with its initial point on the origin, is in the column space. As a matter of fact, I can draw V sub N just as well over here. And we see that V equals V sub R plus V sub N. Okay. Now the question still is, okay, well, but where does this vector end up over here? Okay. Well, how do we know it ends up in the column space, other than what we already know? It's actually quite simple. T of V equals T of VR plus Vn, right? Since V equals VR plus Vn. Well, that equals T of VR plus T of Vn, because this transformation is linear, property of linearity. Okay, T of one vector plus another is T of that one vector plus T of the other. But what's T of Vn? T of Vn is 0 because any vector in the null space is there because it satisfies this equation. And remember, the transformation is defined just in terms of multiply the matrix times the vector. Okay, so that's just T of VR. So wherever VR goes on the column space, that's where V is also going to go. Not only that, but it doesn't take much to see that any vector whose initial point is at the origin and terminal point on this line parallel to the line representing the null space, which is of course perpendicular to the column space, any vector represented by a point on this line is going to go to the same place this does. So that if this specific vector to this point maps, let's say, to this point of the line, and I doubt if it does, I haven't worked out where that point might go. It'd be easy to do, but okay. If this point goes to here, in other words, if the tip of this vector from here to here goes to a vector from here to here, then every point on this line goes to that point. Okay? Just like every point in the null space goes to the origin. Remember, every point in the null space goes to here. Null space collapses to the origin, and any vector along this line collapses to this point, if this really is the point. Now that's an introductory picture to a specific linear mapping. The only thing that's not specific is where this point goes, okay? Now I'm going to actually just, I'm not going to work it out here, but we just multiply the matrix by whatever this vector is. Okay, let's say this vector is 4, 2. Multiply it by this, 4, 2, well, 4, 2 times 4, 2 is 20. Negative 6, negative 3 times 4, 2 is negative 40. So it would be like 20, negative 40. So this point here would actually go down here someplace, but that doesn't change the idea that I'm making here, that that the mapping behaves in this way. Okay, null space goes to the origin. Any vector along this line is going to be the VR vector plus a null space vector. It's going to have to map to the same point as any other point along the line, which would actually be down here, but we can still depict it the way we did.